Mercury, the closest planet to the Sun, presents one of the most captivating puzzles in our solar system. Although small and rocky, this planet harbors significant secrets that challenge our scientific understanding. Its extreme conditions, lack of a significant atmosphere, and proximity to the Sun make it both fascinating and difficult to study. But what makes Mercury so critical for scientific inquiry? To comprehend its importance, we need to delve into the history of its exploration and examine what we've learned so far. Mercury has been known since ancient times, long before the emergence of modern science. Easily visible to the naked eye, it was named after the Roman god Mercury, the swift messenger of the gods, reflecting the planet's rapid journey across the night sky. It is so close to the Sun that it can only be observed during short windows at dawn or dusk, when its brightness is not overwhelmed by sunlight. Behind this fleeting visibility lies a world of extremes, where conditions challenge even the most advanced technology we have developed for space exploration. Mercury's surface, covered in craters, resembles that of our Moon, having been battered by asteroids and comets over billions of years. Without a protective atmosphere to shield it from impacts, every collision with a cosmic body leaves a lasting scar. These craters vary dramatically in size, with some, like the massive Caloris Basin, spanning more than 1,500 kilometers. Apart from craters, Mercury's surface also features impressive cliffs and ridges, known as escarpments, formed as the planet cooled and contracted during its geological history. These features offer a glimpse into the dynamic forces that have shaped the planet over time. One of the most remarkable aspects of Mercury is its extreme temperature fluctuations. During the day, surface temperatures soar to an astonishing 430 degrees Celsius, hot enough to liquefy metals like lead. Yet at night, without an atmosphere to retain heat, temperatures plunge to a frigid 180 degrees Celsius. This stark contrast between day and night serves as a reminder of the essential role an atmosphere plays in regulating the planet's temperature. Mercury's harsh environment gives scientists a glimpse of what Earth might have been like without its atmosphere. Beneath its rugged exterior, Mercury also harbors an intriguing internal structure. Despite its relatively small diameter, just 4,879 kilometers, Mercury has a disproportionately large iron core, which makes up the bulk of its mass. This core may account for the planet's weak, but still detectable, magnetic field, a feature unusual for a planet of its size and composition. Theories suggest that Mercury's large core may be the result of a catastrophic collision early in its history that stripped away much of its outer layers, leaving behind a metallic core enveloped by a thin mantle and crust. Mercury's proximity to the Sun poses a unique challenge for space exploration. In 1973, the Camariner 10TAT spacecraft became the first mission to visit Mercury, providing humanity with its first close-up images. Decades later, NASA's Messenger mission, which orbited the planet from 2011 to 2015, revolutionized our understanding of Mercury. Among its most surprising discoveries was the detection of water ice in permanently shadowed craters near the planet's poles. Despite Mercury's searing daytime heat, these craters never receive sunlight, allowing ice to persist in this otherwise hostile environment. The study of Mercury is critical for more than just understanding this small, enigmatic world. As a planet that formed closest to the Sun, Mercury offers invaluable insights into the early processes of planetary formation in our solar system. Its composition and history may hold clues to the conditions present during the early days of the Sun and its orbiting planets. Understanding Mercury is like deciphering an ancient record that has preserved details about the solar system's evolution, helping us understand the broader mechanisms of planetary development. Although Mercury is unlikely to become a destination for human exploration or colonization, it remains a vital object of scientific investigation. The European Space Agency's BEPIT Colombo mission, launched in 2018, is expected to bring even more discoveries, particularly regarding Mercury's internal structure, chemical makeup, and mysterious magnetic field. As we continue to uncover the secrets of Mercury, we will gain a deeper understanding not only of this small planet, but of the solar system as a whole and our place within it. Mercury, as mysterious and elusive as it may seem, continues to astonish scientists with its peculiar characteristics. One aspect that stands out is its orbital behavior, which sets it apart from the other planets. Mercury's orbit is highly eccentric, meaning it follows an elliptical path rather than a perfect circle. As a result, its distance from the Sun varies significantly over the course of its 88-day year. This short orbital period makes Mercury the fastest planet in the solar system, racing around the Sun at speeds of nearly 47 kilometers per second. This elliptical orbit, combined with Mercury's slow rotation, creates unusual phenomena. One of the most curious features is the planet's day length. A solar day on Mercury, the time it takes for the Sun to return to the same point in the sky, lasts about 176 Earth days, which is twice as long as its year. This means that if you were standing on the surface of Mercury, you would experience extremely long, intense periods of daylight, followed by equally long, freezing nights. This strange relationship between its rotation and orbit has fascinated astronomers and has led to significant advances in our understanding of planetary dynamics. Mercury's gravitational interaction with the Sun also provides a wealth of information about the mechanics of our solar system. The planet's close proximity to the Sun causes it to experience a strong gravitational pull, which affects the shape of its orbit. Over time, this gravitational influence has caused a gradual shift in the orientation of Mercury's orbit, an effect known as precession. Interestingly, the precession of Mercury's orbit played a crucial role in confirming Albert Einstein's theory of general relativity. In the early 20th century, astronomers noticed that the rate of Mercury's orbital precession could not be fully explained by classical Newtonian physics. Einstein's theory, however, accounted for the additional precession, providing one of the first observational confirmations of the theory and forever linking Mercury with the broader understanding of space-time. Yet, despite the progress made in understanding Mercury, many questions remain unanswered. For example, scientists are still trying to determine why Mercury's surface is darker than expected. The planet reflects less sunlight than the Moon, despite having a similar rocky composition. Some researchers believe this may be due to the presence of carbon-rich material, possibly deposited by comets or formed through volcanic processes early in the planet's history. This enigmatic dark surface adds another layer of complexity to Mercury's story, challenging scientists to rethink their models of planetary formation and evolution. Volcanism on Mercury is another intriguing aspect that has captured the attention of researchers. Early observations from the Sponge Plains spacecraft revealed evidence of ancient lava plains that once covered vast regions of the planet. These volcanic plains suggest that Mercury was geologically active for a significant portion of its early history. However, unlike Earth, where plate tectonics continue to shape the surface, Mercury's volcanic activity appears to have ceased billions of years ago. Understanding the timeline of this activity and its role when shaping the planet's surface is a key area of ongoing research. In addition to volcanism, Mercury's magnetic field presents yet another puzzle. While Earth's magnetic field is generated by the movement of molten iron in its outer core, Mercury's field is much weaker and more irregular. This has led scientists to propose that Mercury's core may be partly solidified, with only a thin outer layer of liquid metal remaining to generate the magnetic field. Determining the exact state of Mercury's core will help us understand not only the planet's evolution, but also the broader mechanisms that govern magnetic fields across the solar system. The upcoming Bepi-Colombo mission, a joint venture between the European Space Agency ESA and the Japan Aerospace Exploration Agency JAXA, aims to answer many of these lingering questions. Equipped with advanced instruments designed to map the planet's surface, study its magnetic field, and analyze its composition, Bepi-Colombo is expected to provide unprecedented insights into Mercury's geology and internal structure. As the spacecraft approaches Mercury in the coming years, scientists are eagerly anticipating new data that could reshape our understanding of the small, yet significant world. But why does Mercury matter? Why should we invest time and resources into studying a planet so hostile and seemingly distant from our concerns on Earth? The answer lies in the broader context of planetary science and the quest to understand the origins of the solar system. Mercury, with its unique position near the Sun, serves as a natural laboratory for studying the processes that shaped the early solar nebula, the disk of gas and dust from which all the planets formed. By understanding how Mercury formed and evolved, we gain crucial insights into the forces that shape not only our solar system but potentially other planetary systems in the universe. In many ways, Mercury is a key to unlocking the broader mysteries of planetary formation and the dynamics of solar systems. Its proximity to the Sun provides an extreme environment where we can test our theories about planetary evolution under the influence of intense radiation and gravitational forces. The more we learn about Mercury, the better equipped we are to understand the diversity of planets beyond our solar system and the potential for life in other corners of the universe. As we continue to explore this enigmatic world, we are reminded of the vastness and complexity of the cosmos. Each new discovery brings us closer to understanding the forces that govern not just Mercury, but the universe itself. In the end, Mercury is more than just a small rocky planet orbiting close to the Sun. It is a gateway to the deeper mysteries of the cosmos and a testament to humanity's enduring curiosity. The more we study Mercury, the more we uncover about the grand story of our solar system, and by extension, our own place within the universe. Mercury, despite its small size, continues to hold a disproportionate significance in our understanding of planetary science. Its extremes, from scorching days to frigid nights, from a massive iron core to an almost negligible atmosphere, make it a world of contrasts. But perhaps what makes Mercury truly fascinating is not just its physical characteristics, but the scientific questions it provokes and the answers it helps provide about the formation and evolution of planets, including Earth. One of the most puzzling aspects of Mercury is the process that led to its formation. Traditional models of planetary formation suggest that planets near their stars should have compositions dominated by silicate rocks, as lighter elements tend to be blown away by the intense heat and solar winds of the young Sun. However, Mercury defies these expectations with its enormous iron core. Theories about its formation have evolved over time, and several hypotheses have been proposed to explain its unusual composition. One leading theory is that early in the history of the solar system, Mercury may have been struck by a massive planetary body, stripping away much of its lighter rocky material and leaving behind a dense metallic core. This cataclysmic collision may also explain why Mercury has such a thin mantle and crust, unlike the thicker layers found on Earth or Venus. Another hypothesis suggests that during the formation of the solar system, solar winds may have selectively stripped Mercury of its outer layers, leaving it with a much larger core relative to its size. Regardless of which scenario proves true, studying Mercury provides crucial clues to understanding the violent and chaotic processes that shaped the early solar system. Mercury's extreme conditions, with its proximity to the Sun and lack of atmosphere, also offer a unique opportunity to study space weathering and the effects of solar radiation on planetary surfaces. Over billions of years, Mercury's surface has been bombarded by charged particles from the Sun, cosmic rays, and micrometeoroids, all of which have altered its appearance and composition. These space weathering processes are of great interest to scientists because they offer insight into how planets evolve in harsh environments, and they may even help us understand what happens to other rocky planets around distant stars. The Crescent Messenger mission, which orbited Mercury between 2011 and 2015, was instrumental in advancing our knowledge of space weathering. It discovered that Mercury's surface is rich in volatile elements such as sulfur and potassium, which were unexpected given the planet's proximity to the Sun. These volatile elements should have been lost due to the intense heat, yet their presence suggests that Mercury's surface chemistry is far more complex than previously thought. Additionally, the discovery of hollows, bright, shallow depressions that appear to have formed by the loss of volatile material, suggests that even today Mercury's surface is still being reshaped by space weathering processes. Another key area of interest is the planet's weak magnetic field, which has perplexed scientists since its discovery. Earth's magnetic field is generated by the motion of liquid iron in its outer core, a process known as the dynamo effect. Mercury, despite its large iron core, has a magnetic field that is only about 1% as strong as Earth's. Moreover, Messenger data revealed that Mercury's magnetic field is offset from its center, which has led to speculation that the planet's core is in a state of partial solidification. Understanding why Mercury's magnetic field is so weak and uneven could provide new insights into how planetary dynamos work, and why some planets, like Mars and Venus, have no magnetic fields at all. The upcoming Rebecca-Columbated mission promises to take these investigations even further. With its more advanced instruments, it is expected to provide detailed data on Mercury's magnetic field, internal structure, and surface composition. By studying the planet's magnetic field in greater detail, scientists hope to determine how much of Mercury's core is still liquid and whether the planet's magnetic field is driven by the same dynamo process as Earth's. This data will be crucial in refining our understanding of planetary magnetism, not just for Mercury, but for all terrestrial planets, including those that may exist around other stars. While Mercury may not have the allure of being a potential destination for human exploration, its scientific value remains immense. The more we learn about Mercury, the more we are forced to rethink our assumptions about planet formation and evolution. For example, the presence of water ice in Mercury's permanently shadowed craters, despite the planet's proximity to the Sun, raises important questions about the delivery and retention of water in the inner solar system. These discoveries have implications not only for Mercury, but also for our understanding of how water, a critical ingredient for life, may have been distributed throughout the early solar system. Moreover, Mercury serves as a natural laboratory for studying the effects of extreme solar radiation, helping scientists better understand the space environment closer to the Sun. This knowledge is particularly valuable as we explore the potential habitability of exoplanets orbiting close to their parent stars. Understanding how Mercury has weathered billions of years of intense solar radiation could provide important clues about the conditions on planets and other solar systems that orbit in similarly harsh environments. As we continue to explore Mercury through missions like Cape Apicolumbo, we are reminded of how much there is yet to learn about our closest planetary neighbor to the Sun. Each new discovery peels back another layer of mystery, offering fresh insights not only into Mercury itself, but into the broader history of the solar system. Mercury's secrets, once hidden in the blinding glare of the Sun, are gradually being revealed, helping us piece together the complex puzzle of planetary formation. The more we study Mercury, the more we realize that this small, seemingly desolate planet has much to teach us. From its massive iron core and weak magnetic field to its extreme temperatures and volatile surface chemistry, Mercury defies expectations and challenges our understanding of what it means to be a planet. In many ways, Mercury's story is the story of the solar system, a tale of cosmic violence, planetary evolution, and the enduring quest to uncover the secrets of our celestial neighbors. As humanity continues to gaze outward, seeking to understand the vast cosmos, Mercury remains a critical piece of the puzzle, a reminder that even the smallest, most overlooked worlds can hold profound secrets. By studying Mercury, we not only learn about the origins of our own solar system, but also gain a deeper appreciation for the diversity and complexity of planets throughout the universe. In this way, Mercury serves as a gateway to the broader questions that drive planetary science and our understanding of the cosmos. Mercury, though often overshadowed by larger and more dramatic planets like Jupiter or Saturn, holds a unique place in our understanding of the solar system. As the smallest of the 8 planets and the one closest to the Sun, it offers a crucial perspective on the inner workings of our cosmic neighborhood. Its strange features, an oversized iron core, a surface ravaged by impacts, extreme temperature variations, and a mysterious magnetic field make Mercury a prime candidate for studying not just planetary geology, but also the forces that have shaped our solar system for billions of years. The planet's geological history provides a glimpse into the chaotic early days of the solar system. Billions of years ago, the inner planets, including Mercury, were bombarded by debris left over from the formation of the Sun and the planets. This period, known as the Late Heavy Bombardment, saw countless asteroids and comets collide with young planets, carving out the craters and basins that we observe today. Mercury, with its heavily cratered surface, is a window into this ancient time. The planet's lack of significant geological activity, such as plate tectonics or widespread volcanism, has allowed these ancient scars to remain relatively unchanged over billions of years. In this sense, Mercury acts as a kind of fossil, preserving evidence of the solar system's early violent history. But Mercury's surface is not just a static relic of the past. Recent discoveries have shown that the planet may still be undergoing subtle geological changes. One of the most intriguing features of Mercury's surface is the presence of hollows, bright, shallow depressions that seem to be actively forming in some regions. These hollows are thought to form when volatile materials beneath the surface are exposed to the vacuum of space and sublimate, or turn directly from a solid to a gas. This process creates small pits that give the surface a distinctive appearance. The presence of these volatile materials and the ongoing formation of hollows suggests that Mercury's geology is more dynamic than previously thought, raising new questions about the planet's evolution. Mercury's past is also marked by dramatic volcanic activity. Observations from the Furthest mission revealed vast plains of solidified lava, indicating that in its distant past, Mercury was home to widespread volcanic eruptions. These volcanic plains, some of which are over 1 billion years old, suggest that the planet's interior was once much more active. However, unlike Earth, where volcanic activity continues to shape the surface, Mercury's volcanoes have long since gone dormant. Understanding the timeline of this volcanic activity could provide critical clues about the planet's internal structure and how its core has evolved over time. One of the most striking discoveries of the Furthest mission was the presence of large cliffs or scarps that stretch for hundreds of kilometers across Mercury's surface. These scarps are the result of the planet's cooling and contracting over time. As Mercury's core and mantle cooled, the planet shrank slightly, causing the crust to buckle and form these towering cliffs. The scarps are a testament to the long-term cooling of Mercury's interior, a process that likely began soon after the planet's formation. These features offer a glimpse into Mercury's geological evolution and provide evidence that planetary contraction may be a common process among rocky planets. Despite its small size, Mercury's massive iron core gives it a surprisingly high density, second only to Earth in the solar system. This core, which likely makes up around 85% of the planet's volume, is a key factor in the planet's magnetic field. Mercury is one of only 3 terrestrial planets, along with Earth and Ganymede, a moon of Jupiter, that has a global magnetic field. However, Mercury's magnetic field is much weaker than Earth's and is not evenly distributed across the planet. It is offset to the north, meaning that the magnetic field is stronger in the northern hemisphere and weaker in the southern hemisphere. Scientists are still trying to understand why this asymmetry exists and what it reveals about Mercury's core and the dynamics of its magnetic field. The weak magnetic field raises further questions about the state of Mercury's core. Some researchers speculate that only a thin outer layer of the core remains molten, while the rest has solidified. If this is the case, it could explain why Mercury's magnetic field is so weak compared to Earth's. However, the exact structure of Mercury's core remains one of the planet's great mysteries, and future missions such as Bepi-Colombo are expected to shed light on this question. Mercury's magnetic field also plays a role in shaping its interaction with the Sun. The planet's proximity to the Sun means it is constantly bombarded by solar wind, a stream of charged particles emitted by the Sun's outer layers. Mercury's magnetic field helps shield the planet from some of this solar wind, but the weak and uneven field means that the solar wind can still reach the surface in many areas. This constant bombardment by charged particles may contribute to the weathering of the surface and the creation of the bright hollows observed by Messenger und. Understanding how Mercury's magnetic field interacts with the solar wind could provide insights into the behavior of other planets in extreme environments, including exoplanets orbiting close to their parent stars. Mercury's position so close to the Sun also makes it an ideal laboratory for studying how planets interact with their stars. The intense heat and radiation that Mercury experiences are similar to the conditions on many exoplanets that orbit close to their stars, particularly those known as hot Jupiters or super-Earths. By studying Mercury, scientists can better understand how these extreme environments affect planetary atmospheres, surface conditions, and potential habitability. Although Mercury itself is far too harsh to support life, its study can help inform the search for life on planets and other solar systems. Looking ahead, the Bepi-Colombo mission promises to revolutionize our understanding of Mercury. The mission, which consists of 2 spacecraft, one from the European Space Agency ESA and one from the Japan Aerospace Exploration Agency JAXA, is designed to explore Mercury in unprecedented detail. Scheduled to arrive at Mercury in 2025, Bepi-Colombo will map the planet's surface, study its magnetic field, and probe its interior. One of the mission's key goals is to determine the composition of Mercury's surface and to better understand the processes that have shaped it over billions of years. The mission will also seek to resolve some of the lingering questions about the planet's magnetic field, core, and geological activity. The data collected by Zrigla Bepi-Colombo will not only deepen our understanding of Mercury, but will also provide valuable insights into the broader processes that govern planetary formation and evolution. By studying Mercury, we can gain a better understanding of how rocky planets form, how their interiors evolve, and how they interact with their parent stars. These insights are critical as we continue to explore the many exoplanets discovered in recent years and search for signs of life beyond our solar system. In the grand tapestry of the cosmos, Mercury may seem like a small and unremarkable planet, but its extreme environment, unusual composition, and proximity to the Sun make it a key piece in the puzzle of planetary science. As we continue to explore Mercury and unlock its secrets, we are reminded of the interconnectedness of all the planets in our solar system, and by extension, the universe. Through the study of Mercury, we gain a deeper appreciation for the forces that have shaped not only our own world, but the countless other worlds that exist beyond the horizon of our knowledge. Mercury's importance to planetary science cannot be overstated, even though it may seem like a distant, desolate world. Its unique characteristics and position in the solar system provide an exceptional opportunity for us to study the processes that shape not just our planet, but the entire solar system. As missions like Bepicolombo prepare to send back new data, the mysteries that surround this small rocky planet are slowly being unraveled, and with each revelation, Mercury's role in the broader understanding of planetary formation and evolution grows ever more significant. One of the key areas of study as we continue to explore Mercury is its tectonic history, which remains a subject of fascination for geologists and astronomers alike. Unlike Earth, which has active tectonic plates that move and shift, Mercury's surface appears to be shaped by a process known as planetary contraction. As the planet cooled, its iron core solidified and contracted, causing the surface to wrinkle and fold. This process created immense cliffs and ridges that are visible today, some stretching hundreds of kilometers across the planet. These tectonic features, known as lobate scarps, are particularly interesting because they suggest that Mercury is still shrinking, albeit very slowly. This ongoing contraction challenges earlier ideas about how planets cool and solidify over time, and raises questions about what this means for other rocky planets in the solar system. The study of Mercury's tectonic evolution is closely linked to its core dynamics. As mentioned earlier, Mercury has an exceptionally large iron core relative to its size, making up about 85% of the planet's radius. This massive core is not only responsible for the planet's high density, but also for its weak magnetic field. Understanding how Mercury's core behaves, whether it's partially solid or still mostly molten, could provide crucial insights into planetary magnetism, which is key to protecting planets from harmful solar radiation. The fact that Mercury still has a magnetic field, albeit weak and offset, suggests that its core remains at least partially active, a phenomenon that continues to intrigue scientists. Mercury's tenuous exosphere also offers fascinating opportunities for research. Unlike Earth, which has a thick, protective atmosphere, Mercury has only a thin exosphere made up of atoms ejected from its surface by solar radiation and micrometeoroid impacts. This exosphere contains trace amounts of elements such as sodium, potassium, and calcium, which are blown off the planet's surface by the intense solar wind. One of the surprising findings from the Messenger-TARP mission was the detection of water vapor in Mercury's exosphere, likely sourced from cometary impacts or the slow sublimation of ice hidden in permanently shadowed craters near the poles. These polar ice deposits, discovered in regions that never see sunlight, are one of the most surprising revelations about Mercury. Despite the planet's proximity to the Sun, water ice has been found in deep craters where temperatures remain low enough for ice to survive. This discovery has significant implications for our understanding of how water and other volatiles are distributed throughout the solar system. It also raises questions about the history of water delivery in the inner solar system, including to Earth, where comets and asteroids may have played a crucial role in delivering water and other essential compounds for life. Mercury's ice deposits, isolated in such a hostile environment, provide a rare opportunity to study the history of water in a place where conditions are so extreme. The presence of water ice on Mercury also ties into one of the most fundamental questions about the planet's past. How did these volatiles, which are usually lost in the heat of the Sun, survive and accumulate in such a harsh environment? To answer this, scientists are investigating the role that comets and asteroids may have played in depositing these materials on Mercury's surface. This research extends beyond Mercury to address broader questions about how planets acquire water, a key ingredient for life. Understanding the mechanisms that delivered water to Mercury could shed light on the processes that supplied water to Earth, Mars, and even potentially habitable exoplanets in other star systems. Mercury also continues to serve as a critical testing ground for theories of planetary evolution. Because it formed so close to the Sun, it offers a unique perspective on how intense solar radiation and heat affect planetary development. This is especially relevant as astronomers discover more exoplanets that orbit close to their parent stars, planets that, like Mercury, are exposed to extreme temperatures and solar wind. Studying Mercury provides a way to test our models of how such planets evolve over time, particularly in terms of surface erosion, atmospheric loss, and internal dynamics. As we expand our exploration of the solar system and beyond, Mercury serves as a cornerstone in understanding the diversity of planetary environments. Its extreme temperatures, unusual orbit, and complex internal structure make it an invaluable case study for comparative planetology. By comparing Mercury to other planets, especially Earth, we can better grasp the factors that make planets habitable or inhospitable. In particular, Understanding Mercury's lack of a substantial atmosphere and its interactions with the Sun could help us predict the conditions on exoplanets that orbit other stars, where the search for habitable worlds continues to be a central goal of modern astronomy. Despite the hostile conditions on Mercury, the planet has a story to tell, a story that stretches back to the very formation of the solar system. The more we study Mercury, the clearer it becomes that this small planet holds clues to the broader narrative of planetary evolution. It has experienced cataclysmic impacts, periods of intense volcanic activity, and the gradual cooling and contraction of its interior. Its magnetic field, though weak and offset, offers a rare glimpse into the dynamo processes that generate magnetic fields on rocky planets. And its surface, bombarded by solar wind and micrometeoroids, continues to evolve, shaped by the same forces that govern the behavior of planets throughout the cosmos. Mercury is not just a lifeless rock orbiting close to the Sun. It is a dynamic world with a rich history that continues to unfold as we explore it. The ongoing Bepi-Colombitar mission will undoubtedly provide even more insights, helping to refine our understanding of Mercury's magnetic field, core structure, and surface composition. As we uncover these details, we will gain a deeper appreciation of Mercury's role in the solar system's history and its significance for planetary science. In the end, the study of Mercury reminds us that even the smallest, most unassuming planets can offer profound insights into the nature of the universe. It is a testament to the value of exploration, of pushing the boundaries of human knowledge to unlock the secrets of worlds both near and far. Mercury may be a small planet, but it plays a crucial role in the grand story of the solar system, and its study will continue to inform our understanding of planetary science for generations to come. As we continue to probe Mercury's mysteries, we are reminded of the endless curiosity that drives our exploration of the cosmos. A curiosity that will carry us further into the unknown as we seek to answer the most fundamental questions about our place in the universe. Mercury's story is far from over, and each new mission and discovery adds another layer to our understanding of this enigmatic planet. As one of the most extreme environments in the solar system, it offers a unique lens through which we can study the processes that shape planets, both within our system and beyond. The planet's close proximity to the Sun places it in an unforgiving position, exposed to intense solar radiation and temperatures that fluctuate more drastically than any other planet. Yet, in these extremes, Mercury continues to surprise us with clues about the early solar system and the forces that have shaped planetary bodies throughout time. The upcoming data from the Bepi-Colombitar mission, scheduled to arrive at Mercury in 2025, promises to reveal new details about the planet's composition, geological history, and magnetic field. Equipped with cutting-edge instruments, the mission will be able to map Mercury's surface with unprecedented precision, providing more accurate readings of its topography and the distribution of elements across its landscape. It will also help scientists better understand the mysterious processes that continue to shape Mercury's surface today, including the formation of hollows and the presence of water ice in permanently shadowed regions. One of the mission's most significant objectives is to unravel the structure of Mercury's interior. By measuring variations in the planet's gravity field and magnetic field, Bepi-Colombitar will give scientists the ability to infer the composition and state of the planet's core. This could help resolve long-standing questions about why Mercury's magnetic field is so weak and why it is offset toward the northern hemisphere. The mission may also help scientists determine whether Mercury's core is still partially molten, which could provide crucial insights into how magnetic fields are generated in planets more generally. Mercury's magnetic field, while weak compared to Earth's, is nonetheless one of its most intriguing features. Unlike Mars and Venus, which have lost their magnetic fields, Mercury has managed to retain a weak global magnetic field despite its small size and close proximity to the Sun. Understanding why this is the case could shed light on the broader question of how magnetic fields evolve over time and what factors allow some planets to maintain them while others lose them. Since magnetic fields play a critical role in protecting planets from the harmful effects of solar radiation, studying Mercury's magnetic field could also inform our search for habitable planets beyond the solar system. Beyond the technical data that Scrumai and Bepi-Colombitar will collect, Mercury continues to be a world that evokes wonder and challenges our preconceived notions about what a planet should be. It is a planet of contradictions, extremely hot and cold, small but dense, ancient yet still active in surprising ways. Its surface, heavily cratered and scarred, tells a story of violence and bombardment, while its deep, Shadowy craters hide water ice in a place where temperatures can exceed 400 degrees Celsius during the day. These contradictions make Mercury a natural laboratory for studying the limits of planetary formation and evolution, offering a glimpse into the conditions that may exist on rocky planets orbiting other stars. The study of Mercury also has broader implications for understanding the dynamics of our entire solar system. As the closest planet to the Sun, Mercury experiences the full force of the Sun's gravitational pull, as well as its powerful magnetic and radiation fields. This unique position makes Mercury a valuable case study for scientists who want to understand how the Sun's activity affects the planets around it. This is particularly relevant today as astronomers discover more exoplanets orbiting close to their stars, where the conditions might be similar to those on Mercury. Mercury's orbit also holds a special place in the history of science, as it played a pivotal role in the development of one of the most profound theories of the 20th century, Einstein's theory of general relativity. In the 19th century, astronomers noticed that Mercury's orbit did not behave exactly as predicted by Newtonian physics. Specifically, its orbit slowly precessed, or shifted, over time in a way that could not be fully explained by the gravitational influences of other planets. When Einstein published his theory of general relativity in 1915, he showed that the warping of space-time caused by the Sun's massive gravity could account for the discrepancies in Mercury's orbit. This provided one of the first successful tests of general relativity and cemented Mercury's place in the annals of scientific history. In many ways, Mercury continues to challenge the boundaries of our knowledge. Its small size and extreme environment belie its importance in helping scientists refine their models of planetary evolution and dynamics. Its proximity to the Sun makes it an ideal testbed for understanding how planets behave in high radiation environments, which has implications for the study of exoplanets. And its complex internal structure and weak magnetic field offer tantalizing clues about how planets form, cool, and evolve over billions of years. As we look toward the future, Mercury remains a key target for exploration, not just because of its scientific value, but also because it forces us to confront the limits of our technology and our understanding. Exploring Mercury is no easy task. Its proximity to the Sun makes it difficult for spacecraft to reach, and the intense heat and radiation create harsh conditions for scientific instruments. Yet despite these challenges, the scientific community remains committed to uncovering Mercury's secrets, knowing that each new discovery will bring us closer to answering some of the most fundamental questions about the solar system and the universe as a whole. In this sense, Mercury represents the spirit of exploration itself. It is a world that pushes us to our limits both technologically and intellectually, and rewards our curiosity with insights that have the potential to reshape our understanding of the cosmos. In the coming decades, as missions like Adige Bepi Colombo turn more data, and as we continue to refine our models of planetary evolution, Mercury will undoubtedly continue to play a central role in the study of planets and their origins. Perhaps most importantly, Mercury reminds us that even the smallest, most overlooked worlds can hold profound insights. In its extremes, its scorching days and freezing nights, its massive core and fragile exosphere, Mercury offers a microcosm of the broader forces that shape planets throughout the universe. And as we continue to explore, we are reminded that our quest to understand the universe is far from complete. The secrets of Mercury, like those of the cosmos itself, are still waiting to be uncovered, inviting us to keep pushing the boundaries of what we know. In the grand tapestry of planetary exploration, Mercury may be one of the smallest threads, but it is a thread that connects us to some of the deepest questions about the nature of planets, the formation of the solar system, and the evolution of the universe. As we continue to study this enigmatic world, we are not only learning about Mercury, we are learning about ourselves, our planet, and our place in the cosmos. Mercury's journey of discovery reflects humanity's broader quest for knowledge, pushing the boundaries of what we know about the universe. Its extreme environment and unusual characteristics have not only fascinated scientists, but have also become a symbol of how even the most seemingly inhospitable places can reveal profound truths about planetary evolution, solar system dynamics, and the origins of the cosmos itself. As we deepen our exploration of Mercury, one of the most intriguing questions that remains is how this small planet fits into the broader narrative of the solar system's formation. Mercury's unique properties, such as its disproportionately large iron core and thin mantle, suggest that its early history was likely marked by dramatic events. One of the leading hypotheses is that Mercury may have experienced a colossal impact with another planetary body during the early stages of the solar system's formation. This event could have stripped away much of the planet's outer layers, leaving behind the dense metallic core we observe today. Such an impact would also explain the planet's thin crust and its unusual surface composition. Understanding these violent processes not only helps us grasp Mercury's evolution, but also sheds light on the formative years of the entire solar system, when planetary collisions and migrations were commonplace. In fact, studying Mercury's history can provide a window into how other rocky planets, including Earth, may have formed and evolved during this chaotic period. It also allows scientists to refine their models of planet formation, which are increasingly being applied to the study of exoplanets around distant stars. One of the key insights gained from studying Mercury is the role that proximity to a star plays in shaping a planet's evolution. Being so close to the Sun, Mercury is constantly bombarded by intense solar radiation and the solar wind. This proximity has had a profound impact on the planet's surface and atmosphere, and it serves as a natural laboratory for understanding how planets interact with their parent stars. For exoplanet researchers, this is particularly important, as many of the planets discovered in other star systems orbit very close to their stars in environments that are similarly extreme. By studying Mercury, scientists can better predict what conditions might be like on these so-called hot Jupiters and super-Earths, many of which lie within their stars' habitable zones. Mercury's relationship with the Sun has also made it a critical subject for studying solar phenomena and their effects on planetary environments. The solar wind, a stream of charged particles emanating from the Sun, constantly bombards Mercury, interacting with its magnetic field and creating a dynamic space environment around the planet. Studying these interactions can help scientists better understand space weather, which affects not only Mercury but also Earth and other planets. Space weather has a direct impact on satellites, communication systems, and even electrical grids on Earth. So understanding how the Sun's activity influences planetary environments is of great practical importance. Despite its small size and barren landscape, Mercury also serves as a key to understanding the distribution of water and other volatile elements in the inner solar system. The discovery of water ice and permanently shadowed craters near Mercury's poles was one of the most surprising findings of the Messenger mission. Given the planet's proximity to the Sun, scientists did not expect to find ice on Mercury. Yet there it is, hidden in the deep recesses of craters where sunlight never reaches, offering clues about how water and other volatiles may have been delivered to the inner planets. This discovery is particularly exciting because it raises the possibility that similar processes could occur on other planets or moons, where water ice could exist in unexpected places. The presence of water ice on Mercury, along with the detection of volatile elements like sulfur, sodium, and potassium on its surface, suggests that Mercury's geological and chemical history is far more complex than previously thought. These volatiles are believed to have been delivered to Mercury by comets and asteroids over billions of years, slowly accumulating in the planet's shadowed craters and becoming trapped in the coldest regions. This process mirrors what we think happened on Earth, where water was likely delivered by comets and asteroids during the early formation of the planet. By studying Mercury's volatiles, scientists can gain new insights into how these life-essential elements were distributed throughout the early solar system. Mercury's exploration also speaks to the future of planetary science, especially as we continue to look outward and search for habitable worlds beyond our solar system. While Mercury is far from a candidate for human colonization, its extreme environment offers lessons in planetary habitability. Understanding why Mercury lacks a thick atmosphere, why its surface is so dramatically shaped by solar radiation, and why its magnetic field is so weak could provide essential clues for identifying other potentially habitable planets. Planets orbiting in the Goldilocks zone of their stars, where conditions are just right for liquid water to exist, may face similar challenges if they are bombarded by radiation or lose their atmospheres over time. Mercury's ongoing story gives us a foundation to predict how these processes might play out on other worlds. As Rafai Bepi Columbatit approaches Mercury, it will continue the work of Messenger 3 and deliver even more detailed data on the planet's geology, atmosphere, magnetic field, and internal structure. It is equipped with instruments capable of capturing high-resolution images of Mercury's surface, allowing scientists to map its features more precisely. By studying how Mercury's surface has changed over time through tectonic activity, volcanic eruptions, and space weathering, we can gain a clearer picture of the planet's evolution and how it fits into the broader context of planetary science. Perhaps one of the most profound contributions Mercury has made to science is its role in the validation of general relativity. Albert Einstein's theory, which describes how massive objects warp space-time, was famously confirmed through the observation of Mercury's orbit. For years, scientists had noticed that Mercury's orbit did not behave exactly as predicted by Newtonian physics, with a slight but measurable discrepancy in its precession or the gradual shift of its orbital ellipse. When Einstein proposed his theory of general relativity, he showed that the Sun's massive gravitational pull caused space-time to curve, explaining the small but significant deviation in Mercury's orbit. This observation was one of the earliest confirmations of Einstein's theory, and it remains one of the most famous examples of Mercury's importance in the history of science. Looking ahead, Mercury will continue to be a focus of scientific exploration, and not just because of its proximity to the Sun or its unique magnetic field. The study of Mercury offers a lens into the broader mechanisms that govern planetary systems, from the way planets form and evolve to how they interact with their parent stars. Mercury may be small, but it has played an outsized role in shaping our understanding of the universe. As new missions venture closer to this scorching, enigmatic world, we can expect more surprises, more insights, and more connections to the vast and diverse family of planets that populate the cosmos. Mercury reminds us that even in the most unlikely places, science can find beauty, complexity, and meaning. Its harsh, cratered surface hides stories of ancient impacts, volcanic eruptions, and the constant tug of the Sun's gravity. Its magnetic field, though weak and offset, still protects it from the full force of the solar wind. And its history, like our own, is one of survival, of being shaped by forces larger than itself, yet continuing to hold on to its secrets. As we continue to explore Mercury, we are not just learning about a distant planet, we are learning about the processes that shape all planets, including our own. And in that knowledge we find a deeper understanding of our place in the universe. Mercury, though small and often overlooked, has proven to be a vital piece in the puzzle of our solar system. Its extreme environment, unique geology, and proximity to the Sun provide scientists with a natural laboratory for understanding planetary formation, evolution, and dynamics. Through missions like HARP Messenger-Tartant and the upcoming Jawa Bepi Colombo, we continue to unlock the planet's secrets. From its unusual core and magnetic field to the surprising discovery of water ice in its polar craters. Each new finding deepens our understanding not only of Mercury, but of the processes that have shaped all the planets, including Earth. Mercury's story is not just about one isolated world, it is a chapter in the broader narrative of the cosmos. By studying this tiny planet, we gain critical insights into the violent early history of the solar system, the role of solar radiation in planetary evolution, and the distribution of life-essential elements like water across the inner planets. Mercury's extreme conditions offer a glimpse into what might await exoplanets orbiting close to their stars, and its magnetic field holds clues about how planetary dynamos function. In the grand scheme of planetary exploration, Mercury stands as a reminder that even the smallest, most inhospitable worlds can provide profound insights. Its journey from ancient observations to modern scientific missions reflects humanity's enduring curiosity and drive to explore the unknown. As we continue to study this enigmatic planet, we are reminded of the complexity and beauty of the universe, and how each discovery brings us closer to understanding our place within it. Mercury may not be a destination for human colonization or a haven for life, but its significance in planetary science is undeniable. Its mysteries challenge our knowledge, its extremes test our technology, and its proximity to the Sun makes it an invaluable key to unlocking the secrets of our solar system. In studying Mercury, we continue a journey that is as old as human curiosity itself, a journey toward understanding the cosmos and our role within its vast, intricate design.